Welcome back to CS Connect series. Under set theory, we are going to discuss about set identities in this video. The set identities that you learn here, the same kind of laws or the same kind of rules you can apply to other places too, like Boolean algebra identities or in propositional logic. Wherever you want, you can apply this knowledge. What are set identities? We call them as the laws of algebra of sets. Sets under the operations of union, intersection and complement satisfy various laws. So we have to know what are the operations that we can do with the sets. So only after that content you would be able to understand the identities part. So these various laws are also called as identities. What are the different identities that we'll be discussing in this video? Identity laws, domination laws, idempotent laws, complementation law, commutative laws, associative laws, distributive laws, De Morgan laws, complement laws and absorption law. Let's start with the identity laws, but before starting the identity law, we will first see about the universal set and the set A with which we are going to work. The universal set has the following integers 1, 2, 3, 4, 5, 6, 7, 8, 9. We have the set A which has 3 elements 1, 2, 3 and we have an empty set also. How do you represent universal set? We represent this way. We will represent set A using shaded notation and we will represent the empty set without anything inside. So we will start with the identity law. The first law states A intersection universe is equal to A. A intersection universe is, this is the universe and you are going to place A inside the universe means that is going to be the intersection part. Just try to apply the example 1, 2, 3, 4, 5, 6, 7, 8, 9 intersection 1, 2, 3 will give you 1, 2, 3 only. So that way A intersection universe is equal to A. What about A union empty set? This will also give you A. So if you take universe set and inside that you have A and the empty set. So you have to combine 1, 2, 3 union empty set. This will again result in 1, 2, 3. This is what is represented in the Venn diagram 2. So after applying intersection with universe and union with empty set, we will be getting A again. Next we will move on to domination laws. A union universe is equal to universe. When you find union between A and the universal set, you will have the universal set finally. So that is what is represented using shaded region here. So this is 1, 2, 3. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. This A is also a part of the universal set. In fact, when I say universe, even 1, 2, 3 is included there. The complete set of elements will be the result of union. A intersection empty set will give you empty set. So let's take the universal set A and the empty set. What is actually here? The intersection part. What is in the intersection part? Nothing will be there. Because if you have A as 1, 2, 3, empty set is with no element. No element and some element will give you no element in intersection. So ultimately this part will be getting shaded but you will have no elements in common there. So this is empty set, that is denoted by empty curly braces. Next we will get into idempotent laws. Idempotent laws is you are working with A and getting A even after some operation. A union A will give you A only. So 1, 2, 3 union 1, 2, 3 will give you 1, 2, 3 only. Similarly, A intersection A will give you A only. 1, 2, 3 intersection 1, 2, 3 will again give you 1, 2, 3 only. So we will have A is equal to 1, 2, 3 finally. Next is the complementation law. This is also called as involution law. We have taken two sets, A and universal set. We will place A inside the universal set. So what will be available in A's complement? Anything except 1, 2, 3 will be included in the A's complement. So 4, 5, 6, 7, 8, 9 will be included. Complement of A's complement will again give you A. This shaded region will get reversed back to A again. So you are starting with A. When you apply complement, the shaded region goes to the universal part. Again when you apply complement, it gets back to A again. So complement of A's complement will give you A again. 4, 5, 6, 7, 8, 9. When you take complement for this, you will end up with 1, 2, 3. So this will be the complementation law. Next we will get into complement laws. A is placed inside the universal set. What will be A's complement? It will be the shaded region outside A. So if A is going to be 1, 2, 3, A's complement will be 4, 5, 6, 7, 8, 9 based on the universal set we are just taking it. A complement can also be represented by A bar. Now let's take the first complement law. A union A complement is equal to the universal set. So A is this part, A complement is this part. Altogether, when you find the union, what you will get? You will get the universal set. Just apply this to the problem. 1, 2, 3 union, 4, 5, 6, 7, 8, 9 will give you the universal set. When you are applying complement to the complement, that is complementation law. But when you take complement laws, it is about working with the set and its complement. Now we will find the intersection. A intersection A complement will give you empty set. It's because you don't have any common elements between A and A's complement. So empty set representation is this one. By this we mean that A intersection A complement will be empty set. Now we are moving to commutative laws. In commutative law, you will have two sets involved, A and B. Set A is given 1, 2, 3 as elements. Set B is given 4, 5, 6 as elements. When you take A union B, both the regions are shaded. That is, you include 1, 2, 3 as well as 4, 5, 6. What about B union A? There also you will have both the regions to be shaded. In set, we are not worried about the order of elements. We are concerned only about the elements and not their order. In that case, 1, 2, 3, 4, 5, 6 is equal to 4, 5, 6, 1, 2, 3. This is A union B and this is B union A. Both are equal. A union B is equal to B union A. This is what the commutative law is stating. A intersection B will be equal to B intersection A. Here we have set as 1, 2, 3 and 3, 4, 5, 6. When you find A intersection B, you end up with 3. When you find B intersection A, you end up with 3 again. A intersection B and B intersection A are equal. Both have the element 3 in common. Next we will get into associative laws. This time 3 sets are involved. We are just leaving out the universal set. We will work with the 3 sets. We have A, B and C. A union B is represented in this way. So we will merge both the set elements and bring together as 1, 2, 3, 4, 5, 6, 7. Along with this A union B, we have to join C elements also. It means all the elements 1, 2, 3, 4, 5, 6, 7 are already in A union B. Then C has 8 and 9 additionally. So we will take all the elements together. What about B union C? These two regions will be shaded and these two sets will be put under union operation. We will have 3, 4, 5, 6, 7, 8, 9. Now when you have A union B union C, again A has 1 and 2 additionally. So the 3, 4, 5, 6, 7, 8, 9 will come as it is. We get all the elements together in both these manipulation. So the first law will be A union B union C is equal to A union B union C. So this part is explained here and this part is explained here. What about the next law? It is with respect to intersection. First we are going with A intersection B, which is this shaded region. We have 3 and 7 as common elements in A intersection B. When you want to find the intersection of C along with this particular expression, we will get only this part. 3, 7 intersection 7, 8, 9 will give you 7 alone. Now we will go for B intersection C. Only this part will be shaded. In B we have only 7 as common with C. So B intersection C will give you 7. Now we have to find A intersection B intersection C. So this is 1, 2, 3, 7 intersection 7. What is the common element here? 7 is the common element. So what is the associative law? A intersection B intersection C is equal to A intersection B intersection C. Next we are getting into distributive laws. We have 3 sets A, B and C. So first let's take A. Then we will go with B intersection C. What is B intersection C from these two sets? 6 and 7. So we are taking A as the whole 1, 2, 3, 7 and B intersection C as 6, 7. A union B intersection C will shade all the regions of A as well as B intersection C. It's a union operation, so we are going with 1, 2, 3, 6, 7. Now let's take A union B. When you find union between A and B, you will have 1, 2, 3, 4, 5, 6, 7. Find the union between A and C now. 1, 2, 3, 6, 7, 8, 9. Now we have to find the intersection of both these sets. We have 1, 2, 3 in common, then 6 and 7 in common. So overall, the intersection between these two sets will give 1, 2, 3, 6, 7. From this we can conclude A union B intersection C is equal to, apply this union to B first, take the intersection out, then apply the union to C next. So A union B, A union C, this intersection comes out in common. This is what we tried to prove in this Venn diagram. We will see the second distributive law. So let's take A. This time let's take B union C. So this should be A intersection B union C. So applying this inside, we will have A intersection B union A intersection C. Now let's try for A intersection B union C. This is the intersection part. So 1, 2, 3, 7 from A, B union C will give 3, 4, 5, 6, 7, 8, 9. What is the intersection part? 3 and 7 are the intersection part. So we have 3 and 7 here. Now let's go for A intersection B. So we have 3 and 7 in common here. Then we go for A intersection C. We have only 7 in common. If you find the union, the same set of region will get shaded and you will end up with 3, 7 again in the answer. From this we will be able to prove this distributive law. A intersection B union C is equal to A intersection B. This union comes out and A intersection C. Next we are getting into De Morgan's law. Here we will consider universal set, set A and set B again. Let's take A's complement, then we have B's complement. So A's complement is everything other than 1, 2, 3. B's complement will be everything other than 3, 4, 5, 6. Then we will have A union B will merge A and B together. So the union will give 1, 2, 3, 4, 5, 6. What about A intersection B? Between A and B we have only one common element. So we are taking 3 as the intersecting element here. Now we will get into the law. A complement intersection B complement has to be taken. A complement is this one, B complement is this one. What are the intersecting point? We have 7, 8, 9 and 7, 8, 9. Here what is actually the intersecting point? The universe set is the intersecting point. 7, 8, 9 is present in universal set. A complement intersection B complement will be giving this one. What about A union B the whole complement? From here if you take complement also, you will end up with 7, 8, 9. From this we can prove A union B the whole complement is equal to, apply the complement inside, it will be A complement and B complement. Complement of this union operation will turn to intersection. Now let's take A's complement union B's complement with the same set of numbers. Here 4, 5, 6, 7, 8, 9 and here 1, 2, 7, 8, 9. All together you will have 1, 2, 4, 5, 6, 7, 8, 9. Except for the intersecting part, every other region will be shaded. So this intersecting part is element 3. Except 3, every other element will be found in A complement union B complement. What about A intersection B the whole complement? Except 3, all the numbers should be taken. 1, 2, 4, 5, 6, 7, 8, 9. So the diagram also will be in the same way. Intersection is alone shaded here. Except intersection, everything is shaded here. From this we can prove A intersection B the whole complement is equal to A complement union B complement. Apply complement to the sets and then to the operation here. This becomes union and A complement union B complement will be equal to the left hand side. So the De Morgan's law are A union B the whole complement is equal to A complement intersection B complement. A intersection B the whole complement is equal to A complement union B complement. Next we are moving to absorption laws. Let's take A union B. When you combine A and B we get 1, 2, 3, 4, 5, 6. So this is how we will be representing. What about A here? It is 1, 2, 3. when you find the intersection of A and A union B, what will be the intersecting elements? Whatever elements are present in A, that alone will be intersecting. B's elements will not be there. When you want to find the intersection, this B will go completely and you will have only A. So A intersection A union B will give you A only. Next we will take A intersection B and we have A here. Now if you try to apply union operation, again you will end up with A. If the common element is 3, it means it is available in A as well as B. This A already has 3. So A union A intersection B as well as A intersection A union B. Both will give A only. Why is it termed as absorption loss? Because it is absorbing a complete set and A is coming out as the answer. Now we'll have a recap of all the laws together. We have seen the pictorial representation of both the left hand side as well as the right hand side. If you understand the logic behind these laws, I think hereafter you will not have the need to memorize them. Next we will learn about duality. The identities are actually arranged in pairs. This is actually the associative law. How they have arranged the associative law? In pairs. It means one pair is for union, the other pair is for intersection. Similarly, we will take the distributive law. A union B intersection C and A intersection B union C. Suppose E is an equation of set algebra. This is union, this is intersection, this is universal set and this is empty set. How do we get dual of this equation? We have to replace union by intersection, intersection by union, universal set by empty set by universal set. So let me write it clearly. Union has to be replaced by intersection, intersection has to be replaced by union, universal set has to be replaced by empty set has to be replaced by universal set. Let's see the example. The dual of universal set intersection A union B intersection A is equal to A. How do you find the dual? You have to change the universal set to empty set, intersection to union. This A will stay as it is. This union will convert to intersection. This intersection will convert to union. Both these equations will give A only as the answer. So let's try to interpret this actually. Universal set intersection A will give you A. A union B intersection A will again give you A. Similarly, empty set union A will give you A. A intersection B union A will also give you A. So this is just an example of dual. The pairs of laws are duals of each other. If you check the laws, they are duals. Say for example, all the union here are converted to intersection. Similarly, the union here is converted to intersection. Intersection is converted to union. Similarly, union becomes intersection. Intersection becomes union. That's what they have said. The pairs of laws are duals of each other. What is the principle of duality? If any equation E is an identity, then its dual is also an identity. If this is going to be an identity called equation E, then the dual E star is also an identity. So this is the dual of E. So this is the principle of duality. Let's now move on to membership tables. Set identities can also be proved using membership tables. So for proving the set identities only, we are introducing this concept of membership tables. But what is the table about? We can consider each combination of sets that an element can belong to and verify that elements in the same combination of sets belong to both the sets in the identity. When the element is present inside the set, we use 1. When the element is not a part of the set, we will use 0. So now we will just use a membership table to show that this left hand side is equal to this right hand side. So let's take A, B, C. We will take B union C separately. Then we will take the complete LHS as A intersection B union C. Similarly, we will find A intersection B, A intersection C separately, and then take the RHS of the identity in the last column. Now we have to find whether this LHS column and this RHS column are going to be equal. How are we going to use this membership table? We know when the element belongs to a set, it is represented as 1. When element doesn't belong to a set, we represent it using 0. So the first combination will be A has an element, B has an element, and C has an element. B union C will be 1. When the element is present in A and B, but there is no element in C. Here also B union C will be 1. In union, you are going to join the elements from set C and set B. So there is definitely at least one element that is present from set B. In that case, we can mark it as 1. What about the case where A and C elements are present but there is no element present in B? Again, B union C will have 1 because C has an element. We don't worry whether there is an element present in B or not. What about elements that is present in A but not in B and C? B union C will give you 0. So consider the 0 as an empty set. B is also empty, C is also empty. Union of empty and empty will give you empty again. So that's why we are taking it as 0. So you can also consider this to be the existence of an element and this to be something like an empty set. Now this is the combination for the element that is present in A. The same set of combination of B and C will be available when the element is not present in A. So in this case 1 and 1 will give 1 because we are going to consider only B and C. Similarly 1 and 0 will give 1. 0 and 1 will give you 1. 0 and 0 will give you 0. So this is only with respect to B and C. We are not considering A. There are 8 possible values because for the first 4 values we are interpreting B and C. When we took ordered pair, this is what we did. When we had 1, 2 and A, B, for 1 we had A and B, for 2 we had A and B. Similarly, for 1 we are having 1 and 0, for 0 we are having 1 and 0. So this is also going to be 1, 0 set and this is also going to be 1, 0 set. So this A will also be 1, 0. That's why for the first one you are finding the 4 combinations and for the next 0 you are finding the 4 combinations again. Now we have to get into the LHS part. So we have found B union C. For the same set of inputs we have to find A intersection B union C. When the element is present in A as well as in B union C, you can mark it as 1. 1 intersection 1 will give you 1. So similarly we will have 1 and 1 as 1. You have to look A column and B union C column. So this one and this one will also give you 1. What about the element is present in A? So A has some kind of element and B union C, it's an empty set. In this case when you try to take intersection, what will happen? You will have empty set as the answer. This is how you have to interpret with respect to set membership tables. Now let's get into this 0 part. B union C is going to have some elements. If A is going to be empty and intersection operation is going to be applied, irrespective of the value of B union C, you will have zeros everywhere. Now we have got the LHS. So let's start with A intersection B. Wherever you have 1 together, there alone you will have 1 here. Then A is not empty, B is empty. If you want to take intersection, you will end up with empty only. Similarly, everywhere you can find the trace of 0 in one or the other column. That's why all these values can be marked as 0 directly. What about A intersection C? Consider only A and C. You have 1, 1, so it is 1. Similarly, you have 1 and 1 here. So the third row will have 1. Except that you don't have 1 in other places. This is a combo of 1 and 0, so it is 0. It is a combo of 1 and 0, it is 0. And for the last 4 places, whatever value you have in C, all the values of A are 0 only. So which is almost like empty set. So we can mark 0 everywhere. Now what is the operation that we have to do between these two columns? It is an union. Union means at least one set should not be empty. If that is the case, we can mark 1. If both the sets are empty, then we have to mark 0. From the 5th row till the 8th row, both are empty, which states that The union operation will also give you empty set. What about the first row? 1 and 1 will give 1, 1 and 0 will give 1, 0 and 1 will give you 1. If you are very much comfortable with logic kinds of concept, union is OR operation, intersection is AND operation we can say. All we need to know is this is how membership tables are used for sets. So now you can find the columns LHS and RHS are perfectly equal. So we are using membership tables in order to prove these identities that LHS is equal to RHS. I actually used Venn diagrams in the explanation part to prove them that they are equal. Here they have used membership tables for the same purpose. The ways are different but the purpose is same. Now we will get into generalized unions and intersection. So last video we were seeing about set operations where we discussed about union of two sets and intersection of two sets. This is about the union and intersection of many sets. Since union and intersections of sets satisfy associative law, we do not have to use parentheses to indicate which operation comes first. It's because we know this side is equal to this side. Through associative law, we confirm that we need not provide parentheses to indicate which operation comes first. So A union B union C contains those elements that are in at least one of the sets A, B and C. So A union B union C is the complete shaded region that you can see here. A intersection B intersection C contains those elements that are in all of A, B and C. The elements must be present in A, B as well as in C. Only then the common element can be taken as the intersecting element. The union of a collection of sets is the set that contains those elements that are members of at least one set in the collection. It means we are going to add more than 3 sets to the list. We will use the notation A1 union A2 union AN. So what are A1, A2, AN? They are actually sets. This is equal to union of all the sets together, that is the general representation. The union mentions that the members belong to at least one of the sets in the collection. If you take A1, A2 and A3, even if A2 and A3 are not going to have any element, they are going to be empty. If an element is present in A1, the union of A1, A2, A3 will have that element. This denotes the union of the sets A1, A2 to AN. That is what you can see in this expression. The intersection of a collection of sets is the set that contains those elements that are members of all the sets in the collection. If they say it is present only between A1 and A2 and not with A3, A1 intersection, A2 intersection, A3 will not give that intersecting element. So that intersecting element or an element called A must be present in A1, A2 and A3. Only then out of these 3 sets I can pick A as the intersecting element. We can use the notation A1 intersection, A2 intersection, AN. This will denote the intersection of the sets A1, A2 to AN. Here they are talking about union and here they are talking about intersection. So far we worked with A, B or A, B, C. Now they are introducing more number of sets to the list. The number of sets is this n. So A1, A2 till AN. We are going to solve problem in this generalized union and intersection. For that we need this basic understanding. We are now getting into the practice problems of set identities video. The first problem, show that if A, B and C are sets, then A intersection B intersection C, the whole complement is equal to A complement union B complement union C complement. So they have applied the complement inside and converted this intersection to union. We have to prove it in 2 ways. The first way is by showing each side is the subset of the other. What do you mean by one side is subset of the other? We have seen in the previous video, A is a subset of B and B is a subset of A. It means A and B are equal. By saying that each side is a subset of the other side, we can say that both the sides are equal. And the second way is to use a membership table. So let's start with the first way. If we say A has an element 1, A complement has an element 2 in the universal set of 1, 2. When I say 1 belongs to A, what does it mean? 1 does not belong to A complement. Similarly, when I say 2 belongs to A complement means 2 does not belong to A. This is the meaning. The similar way, when they say X belongs to the complement part, then X does not belong to this inside part A intersection B intersection C. X fails to be in at least one of these three sets. Because of that only, we are not able to pick X as the intersecting element. When they say X does not belong to the intersecting part, it means all the three elements don't have that X. That is, X does not belong to A, or X does not belong to B, or X does not belong to C. If we have A is equal to 1, B is equal to 1, 2, C is equal to 3. Here the intersecting element is actually 1. In this case, consider this to be X. X belongs to A, X belongs to B. What about C? X does not belong to C. That is what they have given. It should not belong to A, or it should not belong to B, or it should not belong to C. That is the meaning of this particular expression. This is equivalent to saying, when I say 2 does not belong to A, then 2 automatically belongs to A complement. Similarly, when we say X does not belong to A, we can tell in other way as X belongs to A complement. Similarly, X does not belong to B means X belongs to B complement. If we say X does not belong to C, then it means X belongs to C complement. This OR will be retained as it is. So we are taking an understanding from this side and we are arriving at this particular statement now. Which operation will tell you such a statement? Union operation will state if it belongs to any of the set, that will be enough for appearing in the union result. Now we will take the right hand side. X belongs to A complement union B complement union C complement. From this what we can say, X belongs to A complement, or X belongs to B complement, or X belongs to C complement. If an element belongs to the complement, it means it does not belong to the original set. If 2 belongs to complement, then 2 does not belong to the original set A. From the same example, we are deriving it in this way. So we can say X does not belong to A, or X does not belong to B, or X does not belong to C. At least one of these conditions should be true. If any of the condition is going to turn true, then X cannot be taken as the common element or intersecting element. Since X does not belong to A intersection B intersection C, we can conclude that X can belong to the complement of A intersection B intersection C. This is a kind of descriptive explanation that we can take for this particular problem. But what are the possible objective kinds they can ask you is, they will give you an element like X belongs to A intersection B intersection C, the whole complement. Which of the following can be true? They can tell you X belongs to A, X belongs to A complement, then X belongs to B, X belongs to B complement, and they may ask you to choose one or two options from that. Questions are possible from this explanation. Now we will get into membership table. So we have the 8 set of values here. Now first we have to start with A complement, B complement and C complement. So A complement will be 0, 0, 0, 0. When an element is present in A, the element is not present in complement. Similarly, when the element is not present in A, it is present in the complement. So we are just reversing the zeros and 1 value that is present in the first table. Now we will solve for A intersection B intersection C. Only when you solve this, we can find the complement. What is A intersection B intersection C? The element has to be present in all the 3 sets. Only in this place you will have 1 everywhere. It means X is present here, X is present here, X is present here. Because of that we are marking 1. If you don't have X even in one of the set, it will be 0. That is the condition for intersection. Now we have to find the complement of this particular column. This is the LHS column. What is the complement? Just reverse it. How do we reverse it? When we say x belongs to this particular column, then x does not belong to this particular column. X belongs only to the first row. So only the first row is taken as 0. When x does not belong to the 7 rows, then definitely x belongs to these 7 rows. Now LHS is found here. Now let's compute RHS. What we have to do? We have to take the union. So A complement, B complement, C complement are empty in the first row. That alone will have 0. The rest of the rows, they have at least 1 in one of the sets. C complement is having 1 here, B complement is having 1 here, here only A complement is having 1, here there are 2 sets with 1, here there are 3 sets with 1. Regarding union, what did they say? It's just an OR condition. It should either belong to one or the other set. There is no compulsion that all the sets should have them. So in that case, we can mark 1 everywhere. We found that LHS column is equal to RHS column. So we have proved using the membership table. Next question. Let AI is equal to 1, 2, 3 inside the set till I. For I is equal to 1, 2, 3. Find generalized union and generalized intersection. First we have to know what is inside the set. When we have A1, the value that will be present here is 1. When the value is A2, 1 and 2 will be present there because they have given the range as 1 to I. If I is going to be 1, only 1 will be the only element that is present inside the set. When we say A3, the count goes till 3. 1, 2, 3. When we say A5, the count will be till I. So 1, 2, 3, 4, 5. If I say 1, 2, 3 up to 10, then this is the I which states that it is A10. So they have given the elements that you have to consider for AI set. So there are n number of sets here because the range is from I is equal to 1 to n. Now we know the union of these sets is the set of elements that appear in at least one of them. When you take A1, you have 1. When you take A2, you have 1 as well as another element. When you take A3, you have 1, 2 as well as another element. Which set is having the maximum number of element? The final set is having the maximum number of element. In this case, the sets are increasing. A1 is a subset of A2. This 1 is a subset of 1, 2. A2 is a subset of A3. A3 is a subset of A4. It goes on and everything is a subset of AN. Every element in any of the set is in AN. It means A1, A2, A3, A5, A100, whatever it is, every element is present in this particular set. So the union of the set is given as AN is equal to 1, 2, up to n. This subscript number will be the final number in the set. If it is A10, then the set will have elements like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This number will tell you the final element of the set. The elements in the AN set will be the result of the union operation. What about intersection? Now when you consider the same set, what number can you find in all the sets together? 1 is present in all the sets. So just by looking at these sets, you can find 1 is the intersecting element. The intersection of these sets is the set of elements that appear in all of them. Since A1 is equal to 1, only the number 1 has a chance to be in the intersection. In fact, 1 is the intersection since it is in all of the sets. So A1 set has the element 1 in the set and that will be the intersection point. So the union will be AN and the intersection will be A1. So overall, if they ask you what are the elements present in the union, you have to mark 1 to n. When they ask what are the elements present in the intersection, only 1 is there. Let's get into the next problem. Find generalized union and generalized intersection if for every positive integer I. So let's take AI is equal to, we'll take minus I plus 1, I minus 1 and I. So if you want to take A1, what will be the value? Minus I will be minus 1. Minus 1 plus 1 will give you 0. 1 minus 1 will again give 0, then you will have 1. So you have to not repeat the elements. So that's why I mentioned 0 only one time. What about A2? Minus 2. Minus 2 plus 1 will give minus 1. You have 0, I minus 1. So 2 minus 1 is 1. Then you have 2. As I increases, the set gets larger. A1 is a subset of A2. So they are saying it's a proper subset because it is not going to be equal. Since we have additional elements in A2, we are just mentioning it as proper subset. All the sets are subset of the set of integers. When you take it up to infinity, you are covering all the integers that are present in the set. So how do we represent the set of integers? We have already seen Z is the notation. So every integer is included eventually. The generalized union will be equal to the set of integers which is represented by Z. Integer means it will include 0, negative numbers and positive numbers. Now this is the union part. What about the intersection? A1 will be the intersecting part because these three elements are present in all the other sets. Similarly, if you take A3, you will have minus 3, minus 2, minus 1, 0, 1, 2, 3. Even this has minus 1, 0, 1. So definitely this will be the intersection part. So we are done with A. What about B? For A1 we will have minus 1 comma 1. For A2 we will have minus 2 comma 2. All the sets are subsets of the set of integers and every non-zero integer is in exactly one of the sets. When you go for generalized union, you will include all the numbers. Just find A1 union, A2 union, A3. You will have minus 3, minus 2, minus 1, then 1, 2, 3. What is missing in this integer order? 0 is not there. That's why they have mentioned the union as the set of integers Z minus the element 0. The set of integers should actually include negative number, 0 and positive number. Negative number is taken from the first element and positive number is taken from the second element. Do you have any scope for getting 0 in minus I comma I? No. So we are excluding the 0 from the union. What about the intersection? Each pair of these sets are disjoint. Do you find any intersecting element between A1 and A2? No. So no element is common to all of the sets. In that case, generalized intersection will be empty set. You don't have any intersecting elements between A1 and A2. You don't have anything between A2 and A3. This is going to be extended for the other sets too. So B is also done. So far we have dealt with the set elements because this particular notation is about sets. Now we are going to work with intervals. AI is equal to closed interval minus I comma I. That is the set of real numbers x with minus I less than or equal to x less than or equal to I. The positive integer notation is only for this particular I, not for the elements in the set. Now what is this brackets and D you can find like this? What are they actually? They are actually the intervals of real numbers. When they are enclosed in square bracket, it means the value of A is included, the value of B is included. We can say A less than or equal to X less than or equal to B. When you have a parenthesis here, B is not included. So A is less than or equal to X and X is less than B. The equal to symbol is missing here. Now we have this particular bracket near A. It means A is less than X and we have square bracket near B. It means the value of B is included. X is less than or equal to B. What about this particular brackets in both the places? The value of A and B are not included. A less than X, X is less than B. So from this question we can understand minus I is included, I is included. But in D, I is included. Infinity is not included, but the previous number is included. So that's why they have mentioned the set of real numbers with x greater than or equal to I. They have not mentioned about the infinity part. This is called closed interval when you include both the numbers. And this is called open interval when you don't include both these numbers. Let's start solving the problem now. Let's take C. Minus I comma I. What is this actually? Minus I2 plus I. A1 is equal to minus 1, 0, 1. So from minus I to plus I means from -1 to +1 the range should run. What about A2? -2, -1, 0, 1, 2. So if I is equal to 1, the range should be -1 to 1. If I is equal to 2, the range should be -2 to 2. This question is quite similar to the one we saw in A, this particular problem. Therefore, the generalized union will be the set of all real numbers. This will be the range with respect to integer. But when we say it's real number, even points can be included. -1, -0.50, then 0.51. It can be included. Here they have given it is a set of real number. When I say it is -1 to 1, I can have -1, -0.5, 0, 0.5, 1. Fractional values are very much possible. So here you have to conclude the generalized union as R, the set of real numbers. What about the generalized intersection? The generalized intersection will have A1 set definitely, and they have given it in the closed interval form of -1 to 1. We are representing it using interval. -1 to 1 can include -1, -0.5, -0.1, 0, then 0.1. It goes on till 1. When you take A2, it will become -2 to 2. So A1 will be definitely included in the A2 set. The interval of all real numbers between -1 and 1 inclusive. It means you have to include these two numbers also. So this is the generalized intersection. Now the final problem. This is closed interval symbol and this is open interval symbol. Here we can take this as I is less than or equal to x and x is less than infinity. So that is what they have mentioned. X is greater than or equal to I. So we have to start with I. It is equal to x. At the same time, that x value will be less than infinity, not equal to infinity. This time the sets are getting smaller as I increases. Because when you are going to start with 1 to infinity, you will have lot of numbers. When you are going to start with 1000 to infinity, definitely you will have lesser range compared to this particular range. This is I is equal to 1 and this is I is equal to 1000. A4 will be a subset to A3, A3 will be subset to A2, A2 will be a subset to A1. This is what they have mentioned by means of getting smaller. So let's take A1. It is 1 to infinity. When you take A2, it is 2 to infinity. When you take A3, it is 3 to infinity. Which is a broad range here. You have 1, 2, 3, 4 up to infinity. If 3 to infinity is going to be A3, 2 to infinity is going to be A2, 1 to infinity is going to be A1, which is going to have a large range here. A1 is going to have the large range here. So we say A3 is a proper subset to A2 because it is including from 2 to infinity. Then A2 is a proper subset of A1 because it is including 1 to infinity. 1 to infinity means 2 to infinity is also covered in that. Because A1 includes all the others, generalized union will be A1. All real numbers greater than or equal to 1 will be taken in this context. It is given with 1 because it is greater than or equal to, and less than infinity is what we are taking from the question. We are just substituting I as 1. So this particular A1 will have a broader range, so that will be the generalized union answer. What about intersection? Every number eventually gets excluded as I increases. Before infinity there will be a number. Let's take it to be some p. Now you have 1, 2, 3, 4. When you move to A2 you are leaving 1. When you move to A3 you are leaving 2. Similarly when you come to this p you will leave all the other numbers. What is there in intersection? Nothing will be there. That is what they say. Every number eventually gets excluded as I increases. When you near infinity, the generalized intersection point will be empty set. With this, we are actually coming to the end of this video. I'll meet you in the next video. Thank you, viewers.